Have you ever wondered what makes a diamond just so incredibly tough? I mean, it's the hardest substance on Earth, pretty much indestructible. Well, it's not magic. It's actually something way cooler, a perfect feat of atomic engineering. So let's dive in and uncover the atomic blueprint that gives diamond its legendary strength.
Right, so the secret isn't really about the immense pressure that forms them deep in the Earth. That's just part of the story. The real answer is hidden deep inside their atomic structure. It's all about the unbreakable way every single atom is connected to its neighbors. You've probably heard of the Mohs scale of mineral hardness, right? Well, diamond scores a perfect 10. It is the undisputed champion. But to really get why, we've got to ask a more basic question first. What does hardness even mean? Okay, so in simple terms, hardness is just how well a material resists being scratched or bent out of shape. And diamond's ability to do this, it's completely off the charts. The whole reason for this superpower lies in how it's built, atom by tiny atom. Scientists have a great term for this. They call diamond a giant molecular structure. And that's our first big clue. It means the entire crystal isn't just a jumble of atoms sitting next to each other. No, it acts like one single massive, perfectly interconnected molecule. Let's zoom in and see how that works. To understand the fortress, we have to start with the single brick it's built from, and that's the humble carbon atom. Seriously, everything that makes a diamond so special begins right here with this one element. Now, diamond is what's called an allotrope of carbon, just like this soft gray graphite in your pencil. The game-changing difference is all in the arrangement. A carbon atom has 4 electrons in its outer shell, just ready to form bonds. These 4 little electrons, they're the heroes of our story. So to build its fortress, the carbon atom does something really clever called sp3 hybridization. Just imagine it has a few different types of tools in its toolbox, but for this very specific job, it needs 4 identical, super strong wrenches. Hybridization is basically the process of melting down those different tools and recasting them into 4 perfect, identical attachment points. And the result of this process? It's pure geometric perfection. Those 4 bonding points, they arrange themselves into what's called a tetrahedron. Think of it like a 3D pyramid. This shape is the fundamental blueprint for all of diamond's legendary stability. And get this, the angle between each and every bond is a precise 109.5 degrees. That number is absolutely key. It's the perfect angle to maximize stability and make sure there are absolutely no weak points anywhere in the structure. It's nature's perfect geometry. Okay, so we've got the perfect atomic building block. But how does this one tiny shape scale up to create an entire diamond? This, right here, is where the true genius of the design is revealed. This leads to a pretty mind-bending concept. The entire diamond, the one you can actually hold in your hand, it essentially behaves as one single massive molecule. There are no seams, no joints, just an unbroken, continuous network of carbon atoms. The rule is simple, but it is incredibly powerful. Every single carbon atom is bonded to 4, and only 4 other carbon atoms. And these aren't weak links either. They are covalent bonds, which are the strongest type of chemical bond there is. The whole process is just so elegant. You have one carbon atom that connects to 4 neighbors, forming that perfect tetrahedron. Then each of those neighbors connects to 3 more, and that pattern just repeats and repeats and repeats endlessly in every direction, building out this incredible network. What's more, the distance between any 2 of these bonded carbon atoms is a totally uniform 154 picometers. That's incredibly short, and it's consistent throughout the entire crystal. It pulls all the atoms into this tightly packed, rigid, and just unyielding lattice. So we have the atomic blueprint. Now for the payoff. Let's see exactly how this microscopic structure creates the amazing properties we see in the real world, from its incredible hardness to how it behaves with heat and even electricity. So why is it so ridiculously hard to scratch a diamond? Well, think about it. To scratch it, you'd have to physically break these unbelievably strong covalent bonds. And since the bonds form this continuous 3D network, there's no easy path, no weak point to exploit. You're literally fighting the strength of the entire crystal all at once. And that exact same logic explains its insane melting point, around 4,000 degrees Celsius. To put that in perspective, that's more than twice as hot as molten lava. To melt a diamond, you have to pump in enough energy to make the atoms literally shake themselves apart from this perfect structure.
And because there are billions upon billions of these powerful covalent bonds all holding everything together, it takes an absolutely immense amount of heat energy to overcome them. The very structure that makes it hard also makes it incredibly resistant to heat.
But here's where it gets really interesting. This perfect structure has a fascinating side effect. Remember graphite? Diamond's carbon sibling? The stuff in your pencil? It's an excellent electrical conductor. Diamond, on the other hand, is a superb insulator. So how can the very same atom behave so differently?
Well, it all comes down to those electrons we talked about. For electricity to flow, you need electrons that are free to move around, but in a diamond, all 4 of carbon's outer electrons are locked up, held tightly in those covalent bonds. With no free-roaming electrons to carry a current, it's a perfect insulator. Simple as that.
So there we have it. We've cracked the code. The mystery of diamond's almost mythical strength isn't really a mystery at all. It's the beautiful result of several perfect factors, all coming together at the atomic level. So let's just recap the 3 secrets to its strength. First, you've got the uniquely versatile carbon atom. Second, its amazing ability to form 4 incredibly strong bonds in a perfect tetrahedron shape. And third, repeating that shape over and over to create a continuous 3D network, basically one giant, super strong molecule. And that's the whole story. This elegant, powerful, and surprisingly simple atomic blueprint is precisely what makes diamond the hardest natural substance known to us. It really is a masterclass in structural engineering, just on an atomic scale. And that leaves us with one final powerful thought. If a simple rearrangement of carbon atoms is the difference between soft pencil lead and a diamond, what other incredible secrets are just waiting to be discovered, hiding in the atomic structures of all the materials that surround us every day?